Okay, so today we're going to finish up chapter 3. So we'll talk a little bit about some theorems about even numbers, odd numbers. We'll define rational, irrational numbers, and then we'll talk a little bit about modular arithmetic. So it's sort of a hodgepodge. So let's just evenness, rationals, modular arithmetic, and the division theorem. Okay, then next time we're going to start chapter 4, and I'll spend, I don't know, maybe 3 or 4 lectures or so on induction, which is the first 2 sections of chapter 4. Okay, so I'll start today with a theorem, which will prove let n be an integer, then n is even if and only if n squared is even. Okay, so one note here is sometimes people in shorthand, instead of writing if and only if, we'll write IFF. So if you ever see IFF, that's shorthand for if and only if. And of course, again, doesn't appear in really formal mathematical writing. But if you're taking notes or working through something on Scratch or something like this, it's a handy way to write it down. So whenever I see if and only if, I'm tempted to write IFF. In a proofwriting class, in a lecture, I should write out the whole phrase if and only if. Okay, so we've maybe already discussed this before, but in order to prove if and only if, right, so this is just, I'll make this a remark. So to prove P if and only if Q, right, we know that P if and only if Q is logically equivalent to if P then Q and if Q then P. It's the thing that we learned long ago in like week 1. So when you're proving an if and only if, you can first prove P implies Q and then prove Q implies P. In other words, you can prove the directions separately, the 2 directions separately, which we've already done several times. So, but I don't think I actually wrote it down the first time we did it. So we can prove each direction separately. If you prove one direction and the other direction are both true, it proves the if and only. Okay, so as always, it's nice to give your reader a little bit of a hint as to what you're doing. So I need to prove if n is even, then n squared is even. So suppose n is even. What does that mean? To say that n is even just means that it's 2 times some integer. So by definition, there exists an integer k such that n is equal to 2 times k. Because that's what it means to say that n is even. Okay, hence, what I'm interested in, I want to know about n squared. I would like to show that n squared is even. I want to show that n squared is 2 times an integer. Okay, so let me do it this way. N squared is just n times n, which means that it's 2k times n, which is 2 times kn by associativity. So n squared is 2 times something. I need to make sure that that something is an integer, right? But by closure of z, kn is an integer. Hence, n squared is even by definition. Okay, so I've gotten various questions from students that sort of hinge on, how much detail do I need to include in a proof? And one thing is that when we first started writing proofs in this class, several of the proofs were proven directly from the axioms. And if you're proving something directly from the axioms, everything needs to be justified, right? So like in this associativity step, if I'm proving directly from the axioms, I need to say by associativity, this equality holds, right? But we're now past that point, unless I give you a problem that says prove this directly from the axioms. So if you're not asked to prove something directly from the axioms, you can do things like associativity, like commutativity, substitution into equalities, these things are sort of all okay. As long as like everybody else in the class would understand the reasoning for why something is allowed. Okay. So unless I say prove directly from the axioms, you don't need to prove directly from the axioms because that would be a little bit tedious. Okay, now I want to prove the converse. If n squared is even, then n is even. Okay, but this is maybe a little bit more difficult, right? Because the first direction, n was even, so I can write it as 2k, and then n squared is like, I have even more 2's available. So there's sort of a very direct way to go, right? By the way, maybe some of you, when you were thinking of this proof, maybe you want to write n squared equals 2k squared, which is equal to 2 times 2k squared eventually. And that's also a reasonable way to go. Right? As always, there's many ways to prove any statement. So I could have done this instead. But in thinking about how to prove this direction, right, if I get n squared equals 2k, then how do I get that n is 2 times something? It seems kind of more difficult, right? This direction, like you somehow have less to work with somehow. But one thing that we can do in a situation like this, so this seems harder to prove. Actually, let me put this in blue because it's sort of a remark. But here we can use a very nice trick, a nice technique. Let's prove the contrapositive instead. Right, so we know that really what I'm trying to prove here is if Q, then P. But we know that this is logically equivalent to if not P, then not Q. And way back when we learned about the contrapositive, I said sometimes not Q, then not P, or the contrapositive is easier to prove because negating P gives you something concrete to work with. Go back and watch the lecture for the proof. Proofs in the pudding. This is exactly one of those cases, because if I assume not P, it means I get to assume that n is odd, and that's a concrete thing that I can work with. Okay, so let's see this. So I'm proving the reverse direction. Again, I need to tell my reader what I'm doing. So we proved the contrapositive. Now my reader knows, okay, I'm doing the reverse direction, but I'm doing it by contrapositive. So suppose that n is not even. Well, we proved that every integer is even or odd, but not both, right? Which means that if n is not even, n's got to be odd, right? Sorry, I just saw a typo in my notes, so I'm trying to fix it. By theorem, therefore n is odd. So by definition, there exists an integer k such that n equals 2k plus 1. That's what it means to be odd. And now we're again in a nice situation because this is something concrete to work with. Hence, n squared equals, well, 2k plus 1 squared, which is 4k squared plus 4k plus 1. Again, you're allowed to do arithmetic like this without justifying every step, as long as it's correct. And this is 2 times 2k squared plus 2k plus 1. So it's 2 times something plus 1. Does that mean it's odd? It means it's odd as long as that something is an integer. But it's a thing that we need to make sure. But that's true by closure of z. 2k squared plus 2k is an integer. Hence, n squared is odd, which completes the proof, right? That's both directions. Okay, so all the blue here are remarks, but the black text here is a complete correct proof that would be acceptable on, say, a homework assignment. Okay, and I mentioned it when we talked about the contrapositive for the first time, and that it would be useful many, many times. which means that I think that in the notes it deserves a red box, right? So let's just call this a technique. It's amongst the simplest techniques proved by contrapositive. So instead of proving if P then Q, prove if not Q then not P. So this is just by the equivalence of the contrapositive to the original conditional, but it's super duper useful. I think well evidenced in this slide. If you tried to prove this without using the contrapositive, it would be a much harder proof, I think. I'm not exactly sure how I would do it. I haven't thought about it. Okay. Now I want to give you a very classic theorem, which also will require a very classic definition. It's, in fact, even something that we've defined a little bit. But let's just say it like this. I want to talk a little bit about rationals and irrationals right now. Here's the definition. Let x be a real number. Then we say that x is rational if there exist integers p and q with q non-zero such that x is equal to p over q, by which we mean pq inverse, right? That's what the fraction bar means. Multiplied by the multiplicative inverse of q, which exists because q is non-zero. So a rational number is just a number that you can write as a fraction of two integers. And we say that x is irrational if it is not rational. Right, which means that every real number is either irrational or rational. But if you have an irrational number, all that means is that you can't write it as a fraction. So it's sort of a little bit of a less constructive definition of irrational. Okay, so I mean, I think technically we've already made this definition as well, but not maybe in a definition box in your notes. So it's worth stating extremely clearly. And of course, rationals and irrationals are extremely important. I mean, the rationality or irrationality of real numbers is an extremely important concept in mathematics. You'll see this in your future math courses. But whenever you learn the definition of rational and irrational, you should learn maybe the most classic theorem about rationality and irrationality. Okay, so one thing that's not that clear from this definition, just from the definition, is whether or not there exist any irrational numbers. Right, because again, it's a non-constructive definition. Maybe you could write every single real number as the fraction of two integers. Maybe, right? There's nothing in this definition that says that there are any rational numbers. Sorry, irrational numbers. We definitely know that there are rational numbers, right? 1 over 2, 1/2, that's a rational number. I don't know if there's any irrational numbers yet. You probably know about some irrational numbers, right? So you know that pi is irrational, but how could you prove that pi is irrational? That it's not possible to write it as a fraction of two numbers? It's not that easy or obvious, right? Another thing that you maybe know is irrational is the square root of 2. But again, how do you know that the square root of 2 is irrational? Well, we'll prove it in a second, but there's like a potentially apocryphal story about this. You can Wikipedia it. So it's a mathematical legend. But the Greek mathematician Pythagoras had like, who you know from the Pythagorean theorem, had like a whole school of people who studied under him. And the Pythagoreans supposedly didn't believe in the existence of irrational numbers, right? Because it's not obvious that any numbers are irrational. Right? How do you prove that pi is irrational? I don't know. Maybe it's rational and you just haven't figured out what the fraction is yet. And of course, they knew about the number, the square root of 2, because the ancient Greeks were, turbo good at geometry. So root 2 is a natural quantity in geometry. It's the diagonal of the unit square, right? So if these side lengths have the unit 1, then this diagonal length has the square of 2. And they believed that it was rational, but they didn't know what the fraction was. So rational. If so, what's the fraction? And according to legend, Hippasus, who is actually a real person, I looked it up, although not much is known about him, but supposedly he discovered a proof that root 2 is irrational, but then when he revealed it to the Pythagoreans, they drowned him in the ocean for basically heresy. So you can search Wikipedia for the story. So Hippasus, he proved that root 2 is irrational and then got killed. Very dangerous to do mathematics. And so we'll prove this. This is one of the most classic theorems in mathematics that you learn when you learn how to prove things. Let's leave that slide kind of bleak. Let's say the real number square root of 2 is irrational. This will be our first irrational number that we really know is irrational. Okay. So first of all, what do we mean by square root of 2? Because I haven't defined the symbol. So by this, I mean the positive real number y such that y squared equals 2. Okay, so I mean, maybe we haven't actually proved it, but you can prove that there is such a positive real number. So you know that you can show that this number exists, but whether or not it's rational, you don't know yet. Now, how can I prove that this number, this square root of 2, is irrational? I need to prove that it's impossible to write it as a fraction of 2 integers. How do I prove that something is irrational? How do I prove that anything is irrational? I need to prove that root 2 can never be written as a fraction of 2 integers. Which is kind of a daunting thing, right? Because there's tons and tons of integers. Again, maybe I just haven't found the correct fraction. So whenever you come into a situation like this where it's not clear how to proceed, you should try to think through your proof techniques that you have, of which we have now several. And I would say that in this situation, it seems really reasonable to try a proof by contradiction. Let's suppose that root 2 is rational and arrive at a contradiction. Why is that reasonable? Because if I assume that root 2 is rational, yet again, it gives me something concrete. I can write root 2 as p over q for some integers p and q, and then I can actually work with those integers. What I'm trying to sort of get at here is, if you're not sure how to prove something, which will happen frequently in your mathematical lives, you shouldn't like freak out, which is a natural reaction to not know how to do something. You should take stock of the situation, think about the tools that you have, and sort of methodically generate ideas and then try them. So I didn't know how to start proving this, but a very reasonable idea seems to be, let's prove this by contradiction, and let's see where we go. So we prove this by contradiction. Right, so suppose for contradiction that the square root of 2 is rational. Now, if I reach a contradiction, I know I'll have proven my theorem that root 2 is irrational. Well, why do we do this? We do this because it gives us something concrete to work with. Then there exist integers p and q with q not equal to 0, such that square root of 2 is equal to p divided by q. Or another way to say this, right? 2 is equal to p over q squared. Hence, we can do some basic arithmetic here then, right? P squared over q squared equals 2, which means that p squared is equal to 2 times q squared. If root 2 is rational, then I have integers like this. P squared equals 2q squared. Okay. Now, one thing that I'll note here is note that in choosing P and Q, we had a choice, right? Because if you can write a number as a fraction, you could choose a different fraction by, you can multiply the numerator and denominator by -1. You could multiply them both by 2, and you're not going to change the fraction. So there's a choice here. And what I'm going to do is I'm going to assume that we made a very nice choice. So note that in choosing P and Q, we had a choice, but we could certainly choose P to be positive. It's always possible to choose P to be positive as long as the number is not 0. So let's assume that we chose P to be a positive numerator. And then amongst all the possible numerators, there must be a smallest one by the well-ordering property. So further assume by the well-ordering property that P is as small as possible. Right? Every set of positive integers has a minimum element. So let's look at all possible ways to write root 2 as a fraction with a positive numerator, and let's choose the smallest one. So not only have I written root 2 as P over Q, I've written it as P over Q, where P is the smallest possible positive numerator for this fraction. Okay, so this is a little bit technical. This is not obvious, but as you're reading this proof, you just think, okay, I'm going to write root 2 as a fraction with the smallest positive numerator possible. Okay, now, since P squared equals 2Q squared, maybe highlight this instead. Well, one thing we know about P squared is that P squared is even. Since P squared equals 2Q squared, therefore, P squared is even. But that means that P is even by the first theorem we proved today. If n squared is even, then n is even. So by the first theorem from today, therefore, P is even. Hence, there exists an integer k. Okay, so I'm going to use some shorthand here, just because when you have future math classes, your professors will use shorthand at the board. So I'm going to start doing that now with the knowledge that when you write up a homework exercise, you should write it formally in complete sentences. When you're taking notes or when I'm writing something at the board, though, I may use shorthand to make my life easier. Okay? So hence there exists an integer k such that P is equal to 2 times k. That's what it means to say that P is even. Okay, substituting P for 2k for P, we see that 2k squared equals 2q squared. Right? Hence, let's just simplify. 4k squared equals 2k squared, q squared. So 2k squared equals q squared. which means that q squared is even, which means that q is even. Right? By definition, q squared is even. So by the first theorem again, q is even. So if I've written root 2 as an integer, sorry, as a fraction of two integers, p over q, we know that p is even. Whoops. We know that p is even, and we know that q is even. But this is going to be a contradiction, because if p is even and q is even, then I can reduce the fraction by dividing them both by 2 to get a different way to write the square root of 2 as a fraction with a smaller numerator, which contradicts the minimality of p. And so now both p and q are even. So this fraction p over q can be reduced. Let's actually give ourselves a little something to work with, which is write q equals 2 times L for some integer L in Z. Right, so p over q can be reduced to p over q equals 2k over 2L, which is equal to k over L. And k is a positive integer less than p. Right? 2k is a bigger number than k, which means that p is a bigger number than k. But this contradicts that p was the smallest possible numerator. Hence, the square root of 2 is irrational. Okay, so proof by contradiction here. If you could write it as a fraction, then the numerator is even. And then if the numerator is even, the denominator is even. And so to get a contradiction, one thing you need to do is you need to assume that the fraction, basically you're assuming that the fraction is as simplified as possible. It's like at the beginning, I assumed the fraction was as simplified as possible, and then I proved that you could simplify it, which is a contradiction. Okay, very famous theorem, very famous proof. Okay, so last two topics as we finish up chapter 3 are on essentially modular arithmetic, and then a theorem that will be very useful for modular arithmetic. And by the way, we're still going to continue learning more about modular arithmetic just as we learn more proof techniques later. So we're not done with modular arithmetic quite yet. So here's the next theorem. So here we're going to go back to modular arithmetic. Here's a theorem. So let's suppose that a, b, c, and d are integers, and m and n are natural numbers that are bigger than or equal to 1. Because I want to use m and n for my modulus. Here's the theorem. If a is congruent to b mod n, and c is congruent to d mod n, then we have 3 statements. One is that a plus c, one is on a times c, and one is on a to the m. Okay, so what do you think this theorem should be? This theorem is saying if you add A and C, if you think about it, this congruence modulo n is something kind of like equality, but not equality, right? So this part is saying something like, oh, A and B are like the same, even though they're not the same, and C and D are like the same, at least from a modulo n perspective. So if I add A and C, that should be the same thing as adding B to D. It should be, right? If this congruence modulo n is something like equality, and this theorem says that B plus D is congruent to A plus C modulo n. Again, this is not going to be equality, right? A and B might be different numbers, C and D might be different numbers, just equivalent modulo n. But if you add A and C, or if you add B and D, those could be two different numbers, but they'll be the same modulo n. Same thing if you multiply A and C. And then same thing if you raise A to a power. Those are also the same. I guess for M could have been 0 too. That would have been fine, but you know that every integer to the 0 is 1 anyway, so you would actually get equality. So what does this theorem say? This theorem says that you can add, you can multiply, you can raise to powers with equivalences modulo n, right? So like, again, this is in blue, it's a remark, right? So we know that like 3 is congruent to 27 modulo 24. So modulo 24, if I want to do like 27 plus 27, what is that modulo 24? Maybe those are big numbers. Or even, let's say I want to do 27 to the 4th modulo 24. If I only care about the number, the results modulo 24, then I can use the fact that 3 is the same thing as 27. And now this I can actually do. This is 81 mod 24. Right, and then 81, that should be easy enough to figure out what that is. That's 24 times 3 is 72, so that's 9. So what this says is that if you're doing arithmetic modulo n, you can replace numbers with other numbers that they're the same as modulo n, and it won't change your result. That's really what this theorem is saying. So this theorem is saying that you can do arithmetic modulo n. And again, benefits are clear. If you only care about the integer, the answer mod 24, you may as well choose a nicer number to start with, right? I can give you like a very, I mean, this sort of already suggests something, right? But like, if I ask you for 25 to the 2020 modulo 24, that would be a horrible thing to try to do, 25 to the 2020. But modulo 24, 25 is just 1. So this is just congruent to 1 modulo 24. So this says that you can do arithmetic modulo n. Okay. One nice thing about this is that I'm going to leave 1 and 3 as exercises. Maybe I'll even put it on the problem set. So parts 1 and 3 are exercises. But I'll prove 2, and 2 should give you the idea about how to prove a statement like this. So let's prove 2. Okay, so suppose that A is congruent to B mod n, and C is congruent to D mod n. What does this mean? This means that n divides A minus B and n divides C minus D, because that's what it means to say that two numbers are equivalent modulo n. It means that n divides their difference. So by definition, n divides A minus B and n divides C minus D. This is the only thing that I can do with this information, right? This is the only way to start. Now what do I do? Well, to say that n divides a minus b, that means that a minus b is a multiple of n. So hence, there exist integers. Let's call them k1 and k2, such that a minus b is equal to n times k1, and c minus d is equal to n times k2. That's what it means to say that n divides those two numbers. What am I trying to show? What's my goal? My goal is to show that n divides ac minus bd, right? So my goal is to find an integer k3 such that ac minus bd is equal to n times k3. This is what I'm after. So how do I do this? Well, the only thing to do is to try something. So I want to get ac minus bd. What I have is a minus b, and I have c minus d. So how do I get something like this? I'm interested in this, and what I have is this. One thing I could try to do is I could try to multiply this one by c, and multiply this one by b, and see what happens. Okay, so multiplying a minus b equals n k1 by c on both sides yields ac minus bc equals n k1c. Right? Similarly, multiplying c minus d by, or c minus d equals nk2 by b gives bc minus bd equals nk2b. I'm only doing this because I want to get an AC and a BD somewhere in the proceedings, and now I've gotten it. But now, hopefully, you can see that if I add these two quantities together, I'll get AC minus BD. So adding these together, we have AC minus BD equals NK1C plus NK2B, which is N times K1C plus K2B. Now, AC minus BD is N times something, and that something is an integer by closure of the integers because K1, K2, B, and C are all assumed to be integers. So by closure, K1C plus K2B is an integer. Hence, N divides AC minus BD. So AC is congruent to BD modulo N. Okay, again, this is yet another case where if it's not clear what to do, you just got to try something. At the start, I just wrote down what congruence modulo N meant. Then I wrote down what divisibility meant. Those two steps should almost be automatic at this stage, right? If I write down that N divides A minus B, by definition, that means A minus B is equal to N times some integer K1. But then I had to step back and think, okay, well, what do I want? I want N divides AC minus BD. How do I get there? And then if I thought hard about how to get there, eventually what I came up with was let's multiply one by C and let's multiply the other one by B and see what happens. And it gave us what we wanted. So that was good. But when you're doing these homework exercises, sometimes the first thing you try is not going to lead anywhere. You still try, right? So you try some idea, you follow it along the road, you just keep on trying stuff. If it seems to hit a dead end, you can go back and then try something else. You try something else, You talk to your friend, you ask them, oh, what can I possibly try here? Maybe they have some idea, you come talk to me, I'll ask you some questions and you can figure out something to try. I mean, this will be a useful skill in general, but definitely in your future math classes, in homework or on an exam. You got to be comfortable just trying stuff, Okay, and then the last topic for today is the division theorem, which is actually in section 3.5, which I'd like to state because I want to be able to use it, but I'm not going to prove it yet. Okay, so I don't want to prove it yet, but I will eventually prove it in this class. And by eventually, I mean pretty soon, actually. So let me just state it now. It's very important. It's very useful. So let's state a theorem, but not prove it yet. It's the theorem. For all integers a and b with b positive, so with b greater than 0, there exist unique integers q and r such that a equals bq plus r with 0 less than equal to r less than b. Okay. For any integers you choose, a and b, as long as b is positive, there are unique integers, q and r, such that a equals bq plus r with r between 0 and b. Now, what does this theorem mean? If you understand what this theorem means, then you don't need to memorize it because you'll just remember what it is. The variable names here, a, b, q, and r, or at least q and r, are supposed to be chosen suggestively. Q here means or stands for quotient, and r here stands for remainder. What this theorem says is that you can always, that you can divide a by b and get a unique quotient and remainder where you're choosing the remainder to be between 0 and b. So this theorem says you can divide a by b. Not necessarily evenly, you might be left with a remainder, right? So where q is the quotient and r is the remainder. And then, you knew this even since elementary school. There's only one answer if you make sure that the remainder is small enough, right? So you can always get the remainder between 0 and b, less than b. Right? If it's 0, it goes in perfectly evenly, but you might have a remainder of 1 or 2 or 3 or 4 up until b. So if you choose the remainder small enough, right, so less than b, but greater than or equal to 0, then the quotient and remainder are unique. That's what this is saying. Okay, so the uniqueness comes from the fact that you're assuming that the remainder is small enough. Okay, a thing that I should note here is I'm assuming that b is positive, but a can be any integer. So it turns out that you're probably used to thinking about this particular process of dividing. In elementary school, you're used to thinking about it with a and b both positive. But this holds for any a's, right? So let's just look at some examples, right? So if I let A equal 93 and B equal 6, well, we know that you can divide A by B and get 15, I guess. Right, so maybe say 93 equals 6 times 15, that's the quotient, plus 3, that's the usual remainder you choose, right? Of course, you could do 93 equals 6 times 14 plus 9. You could do that, right? 84 plus 9, that's 93. There's more than one way to write A equals BQ plus R. But this remainder is not in the specified range. This remainder is not between 0 and B. And so this is not the Q and the R that the theorem is talking about, right? This theorem is talking about this Q and this R, and you're guaranteed there's a unique one from this theorem. Okay, but you can also do this with negative numbers. So if we let A equals negative 16 and B equals 6, now you need to think about, well, what do I mean by dividing, right? So like, for example, maybe you want to choose 2 here. So negative 16 equals 6 times, negative 2. But then you need to subtract an additional negative 4, which is not the Q and the R specified by this theorem because the remainder is in the wrong place. It's not between 0 and B, right? So if you divide 6 into negative 16, the quotient is actually negative 3, and you have to add 2, but this remainder is in the correct place. Right? So the point of this theorem is just no matter which 2 integers you pick, as long as B is a non-zero positive integer, you can always divide A by B, and you're guaranteed a unique answer if you want the remainder to be in a specified range, which is between 0 and B, including 0 but not including B. Okay, so this theorem will come in very, very useful, and we will prove it, and we'll use it to prove other things. But all it says is something that you already know, which is basically that you can divide integers and get a unique quotient and remainder. That's what it says. All right, so next time, as I said, we'll move on to chapter 4. Right, I've already made the blank slides for chapter 4 here. And yeah, we'll go from there.